Hello, everyone. Welcome to the MIF++ seminar. It's a great pleasure to introduce my colleague, Dr. Sam Coates from the University of Liverpool, the Department of Physics, who will talk about quasi-periodic tilings. Over to you, Sam, please.
Thank you very much. Yeah, I'm going to talk about some specific aspects of quasiperiodic tilings, um, specifically some of the stuff that I've been doing recently in my fellowship. Um, and so I've kind of pitched this seminar in a sort of simplistic style for a couple of reasons. And I've kind of also arranged it so that it's a kind of brief history of quasicrystals and tilings, a little bit of introduction to some of the methods for producing quasiperiodic structures, a demo of some software that I've written, and then a kind of quick pitch for like data science approaches that could use some of the stuff that I'm kind of exploring at the minute. So this seminar, the slides come with a warning that I'm a physicist that is attempting to speak mathematics. I did my PhD in surface science, looking at actual quasicrystalline samples, and kind of got lured into looking at the mathematics of these things in terms of tilings over the years. So the point of making the kind of warning and disclaimer is that take any declarative statements that I make about the maths of these things with a pinch of salt, especially given that I'm being recorded. I don't want to be, have things used in evidence against me in the future. So I'm covering my bases there. So what I wanted to kind of get for me personally out of the seminar is this kind of message or this argument that the real value of quasicrystals isn't actually the materials themselves. It's the geometry that you can use to model the phases, these materials. And so by doing that, I'm going to show one method that we can use to generate quasiperiodic tilings that actually gives us a huge tunable design space, and then make the case as to why a data science approach might be the best way of kind of exploring practical applications of quasiperiodic geometries. And I guess if there's a log line, it would be that quasicrystals themselves aren't useful, but quasiperiodic geometries might be. So what I'm going to do is just give a very brief overview as to what quasiperiodic means, because it has a very specific definition. And again, I don't want people in the field to be angry with me. But this is something that I usually present to undergraduates or maybe people with a passing interest in my work. Is this idea of periodicity versus quasi-periodicity. And I use tilings because I think most people are very familiar with what a tiling is, even if they don't know it, right? If you see something like these squares, you see them in bathrooms all the time, kitchens, whatever. So the idea here is that with a periodic thing, in this case a tiling, we've got long range order guaranteed because we've got a unit cell, which in this case is our square, and then we've got translational symmetry baked into the system. So if you were to take this square, copy it, move it to the left, to the right, up and down, you would tile the infinite plane using these squares as unit cells. And I guess this concept of periodicity is kind of self-evident in that you can imagine what comes next. If I were to ask someone, what would you do by, if I gave you a tile, where would you place it? It would be somewhere on the edges in which you would kind of periodically carry on the pattern. For a quasi-periodic thing, though, we've got the following definition, that we've got something that has long-range order, but has no unit cell and no translational symmetry. And again, this, I think, is a hard concept to get across initially, because I think your brain automatically always looks for repetition. And so you show someone a tiling like this, which would be the Penrose tiling. And the conversations I've had with people is that they're trying to find a way in which it repeats. And so they'll say, well, I can see this kind of collection of 5 tiles here is repeated over here. Yes, that's true, but it is a repeating motif that is not periodic. So if you were to take a copy of the entire tiling and shift it to this point, you would not, in fact, be able to cover every single shape. You would end up with mismatches, and the whole thing would look pretty rough. Likewise, if I were to give someone a set of instructions based on some translations, like moving left or right or up or down, you could not take one of these tiles and apply the same translations over and over again to tile the plane so that it would look like this. And so the idea here is that we've got long-range order, no unit cell, and no translational symmetry. The question then comes up sometimes, if you've got a background in condensed matter physics, is how do you prove that this thing has long-range order? And if we're talking about condensed matter physics stuff, then the measure for order would be a diffraction pattern or a Fourier transform of your points in space. And so here is a nice pattern that I've taken from the Fourier transform of a Penrose tiling. So I've just decorated all of the points on these tiles, all these vertices with atoms, and then taken the Fourier transform just using a bit of Python magic. And what we end up getting is a very nice diffraction pattern. And by nice, I mean that each of these points are discrete. There's a little bit of noise in the image because it's not a perfect Fourier transform. It's a bit kind of quickly calculated. But you can show mathematically, analytically, that each of these points is a pure point in the diffraction spectrum. And thus, the thing that we're taking the transform of, or the diffraction pattern from, must have long-range order. And so the statement would be that all quasicrystals or quasiperiodic tilings will have a discrete diffraction pattern or Fourier transform, and thus will have long-range order despite the lack of translational symmetry and unit cell. Okay, so with that kind of introduction, I figured it'd be best to go back into the history of these materials and explain why I'm no longer interested in necessarily exploring things from the material side of the field. So back in the 80s, Dan Sheckman rapidly cooled down an aluminium manganese melt and measured a 10-fold electron diffraction pattern. Obviously, one of those kind of miracles of mistakes in science where he was just messing around, cooled the thing down and found this pattern. And tried to get it published, but got severe backlash from the community in crystallography because I think Linus Pauling said there are no quasi-crystals, there are only quasi-scientists, arguing that this was not from a single sample, it was a twinning of or multiple structures combining to make this jazzy pattern. But eventually he kind of won the battle and received the Nobel Prize in 2011. And with a representative of the IUCR here, there was a redefinition of what the word crystal means. It used to have to include unit cell and translational symmetry, periodicity. Now it just means a crystal is if it has a diffraction pattern. So if we see these nice pure point spots from a diffraction pattern, then we can say it's a crystal. So ironically enough, we shouldn't actually call them quasicrystals anymore. They are just crystals with quasiperiodic geometry. But anyway, point is that we've developed this field over like 40 years now. And since the discovery in the early 80s, there have been over 100 intermetallic phases discovered. And these phases are very well understood now. So this is in terms of both where the atoms are, what atoms are where, and also how they behave. So all the kind of physical properties that you would ever want to know about a intermetallic sample have been measured. And my old boss, Professor Tamura, spent a lot of time engineering phases carefully so that we could find whether a quasicrystal could superconduct, and it can. Whether it has long-range magnetic order, it does. Likewise, loads of people have looked at electronic transport, thermal transport, all the types of condensed matter properties have been explored, and all the basic physical questions have been answered. So we really do have like a good grasp on what these materials are like. The big question that I'm commonly asked, again, by people that are interested in some of the science, or I'm asked by panel review boards, is, are they useful? Can we make money from them? Can we apply them in some way out in the real world? And so the answer to the question is, are they useful, is no. Essentially, any kind of advantageous property that these intermetallics would have over conventional intermetallics is massively offset by the production cost. So forming these very specific phases at bulk would cost an enormous amount of money and an enormous amount of time versus a very slim kind of advantage. And I think semi-famously, some of the kind of physical properties are also offset by a huge disadvantage. So these materials, for example, have a very low coefficient of friction, meaning that they were once mooted as a good covering for frying pans because they're the best non-stick covering around. The problem is that they also corrode when you expose them to salt. So they make a really bad piece of kitchenware. So yeah, you can fry an egg and it won't stick to the pan, but as soon as you start trying to season the egg, everything falls apart. And there's a similar story over lots of different properties that make these things kind of semi-obsolete in terms of making money from them. So this is where this kind of idea comes in of using geometry as inspiration to hopefully find a useful quasicrystal. And it's not a new idea. It's not an idea that I've come up with, but it's certainly one that definitely could be refined and explored more kind of generally and with I guess, a more considered approach. So it's a trivial statement, but the fabrication of anything arranged in any geometry these days can be applied in any setting at basically any scale. So we can make things, on the meter length scale up to, kilometers of arrangements in the ocean, for example, down to the nanoscale. And we've got precise control over where we build whatever we're building. And this is essentially the field of metamaterials, right? This is kind of the description of that field, which is that we can build things to act in a specific way at a specific length scale. And so the question that I started asking myself is, well, can we use quasiperiodic geometries in this setting and try and apply some of the advantageous properties that may exist in the phases, like take away the actual physical material and then apply just the structure itself? Then the question becomes, are quasiperiodic geometries useful? And the answer to that is yes, but. So I've collected here completely arbitrary, picked randomly from the literature, studies that have looked at quasiperiodic geometries separated from, the alloys or the other phases that we have out there. So there's a couple of papers that look at tilings. There's a couple of papers that are based on three-dimensional models of quasicrystals themselves. And in each of these hand-picked or arbitrarily picked examples, the quasiperiodic geometries outperform periodic geometries in the kind of niche that they're looking at them in. So this first one shows that they perform better at being a stiff lattice, which is good for mechanics. We've got the band gaps are multiple omnidirectional band gaps where periodic structures only produce one type of band gap. The idea being that you have band gaps all over the place, and actually these things act very well as a kind of broadband blocking device. We've got a paper that looks at heat conduction, and you can control heat conduction better using a quasiperiodic system. And then a paper that I was part of last year that looked at using these guys as waveguides to better control the flow of energy on the coast. So looking at what happens when a water wave strikes a waveguide, can we redirect the energy of the wave, block the energy of the wave to help save, for example, the Yorkshire coast on the east of the UK. And it turns out our quasiperiodic systems are better at doing that than a periodic waveguide. So there's plenty of scope for these guys behaving in a way that is advantageous. The but of it all comes from the fact that if you look through the literature, the number of tilings that people have used, the number of quasiperiodic geometries that people have been inspired by to look at the applied side of things is very small. So I'd say less than 10 probably geometries have actually been explored. Typically, you'll be looking at Penrose tilings. These days, people are very excited about the hat tiling, the tiling that is aperiodic but has just one tile. The point being is that, as I'm about to show, the methods that we have available to us to make these geometries actually allow us to make a huge number, possibly infinite, I think probably infinite, And my argument is that instead of relying on the same old specific cases that people look at time and time again, we could actually turn this into a more general system using some data science. So how do we actually go about making these tilings? So there's a couple of different methods. I'm going to focus on one because it's the backbone of this software that I've made, but there are lots of different ways of doing this. This for me is the kind of most accessible and most customizable to the layperson. So it's called the dual grid method, and it's based on, or was published by Nicholas de Bruyne back in the 80s, who was basically trying to parameterize the recently published Penrose tiling at the time. And it's deceptively simple. It's very elegant. It takes a little bit of work to kind of do the whole coding side of things, but once it's working, it's very fast and, like I said, highly customizable. So the idea is that we start with two vectors or two vector families, where we have a set of grid vectors as one family. We'll call these K, J, which are associated with an infinite set of parallel lines, which we'll call a grid. So in this example here, we've got K1 pointing just to the right-hand side. And perpendicular to our vector, we'll have these grid lines which will extend off into infinity. And then the magnitude of our K vector is just defining the separation between these grid lines. That's one family done. The second family would then be the tiling vectors. So these are tiling vectors would be exactly identical orientation to K, but not necessarily the same magnitude. So at the top here, we've got our grid vectors, 1 and 2, and at the bottom, we've got our tiling vectors, 1 and 2. And we've kept the same orientation, but we've increased the magnitude of A1 in the middle here. And then we've kept this increase, but we've decreased the magnitude for K1. And this is all valid stuff. We can play around with these magnitudes as much as we like. And those really are our two ingredients, and that's all we need to use to make kind of any tiling that's based on rhombuses. So the question is, now that we've defined two vectors, what do we do next? So we draw the grids defined by these two vectors, and we overlay them on top of each other. And we end up with a load of points where our grids intersect. And so I've highlighted just the middle point here for this family of grid vectors and tiling vectors. And what we say is that an intersection point between grids will define a tile, and the tile is constructed from the J vectors which are involved in the intersection. In this case, we've only defined two grids. And so we build a rhombic tile based on the two vectors that are involved. 1 and 2 are involved. And so we use tiles vectors 1 and 2 to form this kind of rhombic tile. And the idea is that you go along A1, go along A2, and then you complete the cycle by going negative A1, negative A2. And that's where this rhombus comes from. Do you have a question?
Yeah, Sam, could you clarify? So you're constructing this green cell on the left by using two vectors A1, A2, right? Okay. And the vectors K1, K2 are not yet used.
So they are used only to define the grid lines that we see on the left-hand side. Mm-hmm. So our K1 is just defining the separation of these grid lines.
Okay.
And then our K2 is defining the separation of these grid lines, like so.
Okay, right. So by grid, you mean a collection of parallel lines?
Yeah, exactly. Yeah.
Okay. So a grid is defined by the pair K1, K2, and the unit cell is defined by A1, A2.
Yeah, the tile itself will be defined by doing the cycle of A1 and A2. So A1, A2 minus A1 minus A2.
Okay, so this unit cell and two grids are not yet combined together. At the moment, they're separate.
So they won't ever be combined. They're only, all that we're interested in is where they intersect. And so when they intersect, we draw the point of intersection, and then we look at what grids are involved in that intersection. In this case, because we've only got two grids, 1 and 2, we only have to worry about drawing the tile using vectors 1 and 2.
Okay. Okay. So in the second picture, the two grids are the same.
Yes.
Visually.
Yes. So in this case, we've still kept the same grid vectors. So our magnitude is still exactly the same in our first example, but then I've scaled down one vector, A1, in our tiling space. And so when we then try to build the tile out of these vectors, we get a smaller tile in one dimension.
Okay, so we haven't started yet to build tiles. Right?
No, sorry, yeah. No,
right.
So this would be just, this would be making one tile out of one intersection point at this point.
Okay, right.
And so in this case, we've looked at a regular intersection. And so this is where we've only got two grids meeting. And in this case, we always form a rhombus. If we have any more than two grids meeting at exactly the same point, then we end up finding a polygon, so 2 times n. So if we had 3 grids, which I'll get onto, then we'll find a hexagon, for example.
I see.
Yeah. And so in this case, we've looked at one intersection point forming one tile. But if we then just do this for all intersection points, then we end up forming a tiling. So in this case, we've kept the original scales from the left-hand side with this green guy. And then we're looking at all the intersection points of our two grid families, and then drawing a tile at each of these points, and then stitching everything together at the end.
So you put a tile, the center of a tile simply at each blue point.
Yeah, I mean, so technically, there are a couple of different ways in which you can kind of algorithmically find out where the tile should be placed in real space or tiling space. But when I originally kind of came across this method, tried it for myself, I would draw the tile vertex, their origin at each intersection point, like so. And then I would stitch everything together. So I know, for example, that this intersection point, which makes a tile, has to be connected to this one. And so you would literally slide them all together. And then you slide them in the other direction as well. And it's a very long-winded process, and it's a really bad way of doing it.
You mean slide two tiles?
Yeah. So it's literally cut like just, I know from construction in the grids that an adjacent point along this intersection, along this grid, they have to be connected in tiling space. But if you were to draw a rhombus on each point, they wouldn't actually be connected in this kind of construction. So you can either slide them all together bit by bit, or there's a bit that I've left out of the dual grid construction where you actually index the space surrounding each vertex. So in this case, we'd have a 0, 0 space, a 1, 0 space, a 1, 1 space, and then a 0, 1 space. You use your tiling vectors to take the dot product with those indices, and you find the vertices in tiling space, and then you link everything together. And that gives you an immediate tiling without having to slide everything together. So I skipped out that bit because I thought it might be too confusing to include, but maybe I should have included it.
Yeah. I encourage everyone to ask questions because
please do, because I'm aware that I may skip over stuff. But the point here is that we've defined this kind of boring set of grids, two vectors, looked at the intersection points, and we can plot where everything connects to make a boring rhombus tiling in this case. To make it a bit more interesting, we can add a third vector, so a third set of grids, and introduce a new parameter to play with as well. And so in this case, I've just defined a third vector at 60 degrees relative to K2. And so we end up with this kind of hexagonal set of grids. Now that we've got at least 3 grids, we can actually start playing by shifting the grids themselves around. So this means if I was to take the vertical grid set like this, I physically move them in grid space, left and right, based on some shift parameter. So we have a value of fj between 0 and 1, and lj is the magnitude of the grid vector. So if I were to take this vertical set of grids and shift it all the way to the right, that would be a shift of f is equal to 1. If we shifted it half the magnitude, it would be f is a half. as we shift these grids around, what's happening is the intersection points are changing. And as the intersection points are changing, the tiling that we would create eventually is also changing in terms of its local geometry and some of the other parameters that I'll talk about. What we'll do here is say that we've got a family of 3 grid vectors and 3 tiling vectors. And that means we've got a family of 3 shifts as well that we could apply individually to each of these grids. But we'll collect them all together and say that the sum of the shifts, these 3 shifts, we'll call alpha. So if I were to simply draw all the grid lines for our family of 3 vectors and apply 0 shifts to them all, we would end up with a situation like this, where each of our intersection points has 3 grids going through it. If the sum of the shifts on these 3 grids is 0.5, then you can see that the geometry of the actual grid lines is changing, which means the intersection points is also changing. And so if we make our tilings from these grids and these intersection points, we end up with something like this. So on the left-hand side, with alpha is 0, we had 3 grids meeting at each point, which means each of our tiles has to have 6 sides. We find a kind of honeycomb lattice, each made with our hexagons. On the other hand, where we have only 2 grids meeting at each intersection point, we form a rhombus, and in this case, we end up with the dice lattice. And so here we've got this shift parameter that will change how our grids intersect, which then changes the geometry of the tiles that we want to be looking at. So how do we actually go about making quasi-periodic versions of these tilings? First, we can look at some of the things that we're controlling. So I've introduced these vector family grid vectors and tiling vectors, and we can affect the orientations as long as they're all identical. The grid vector equals the tiling vector orientation, but we can change the relative scale of these vectors as well, which is something that I showed. Changing these vector families to whatever kind of customization you want will affect the symmetry of these things. It will affect individual tile geometry. It affects tile placement. The idea here being that if you were to shorten a grid vector relative to all the other grid vectors, you would be crossing more grids because the distance between each grid line is shorter. And so you'd have a more dense set of grid lines. That means you'd have more tiles corresponding to those grid lines. It also affects the tile frequency as well in a similar kind of logic. Then we have the second parameter that we can also change, which is alpha, our sum of our shifts. This will also affect tile geometry, tile placement, and the vertex types in the tiling. So this is where tiles will meet and their frequency. So with this quasi-periodic example that I've got here, a vertex type might be where the red and green hexagon meet with these 2 parallelograms, these 2 rhombuses even. That would be one vertex type. By shifting alpha, we can change the different vertex types and their frequencies across the tiling. So let's actually make some quasi-periodic tilings by controlling both of these parameters.
Sam, could also check before we go to more examples.
Yeah.
How do you actually construct the shape of a single tile?
So in this case, it would be, if we go back to here, it's based just on the kind of positive A1, positive A2, negative A1, negative A2. So that's all it is. It's just a cycle that you walk around based on if these are grid vectors, if these are grid lines 1 and 2, we use tiling vectors 1 and 2 to complete that cycle.
So in this case, a tile is a parallelogram.
Yes, in this case, yeah.
Okay, but sometimes your tile is a hexagon.
Yes, so if it's a hexagon, that's where we've got 3 grids meeting at exactly the same point.
Okay, so on the right-hand side, I see. Okay, so we have 3 grids meeting at every point.
Yeah.
And how exactly do we get a hexagon?
So in that case, I know that in this case, we've got grids 1, 2, and 3 meeting at that point, which means that I know that vectors A1, 2, and 3 are involved in making a tile, in which case we do the exact same thing before. We walk along half the way, so A1 plus A2 plus A3, and then we complete the kind of circle, or hexagon in this case.
Uh-huh, I see.
And we do the same thing for, it doesn't have to be a hexagon, it could be a nonagon or decagon, etc.
So in case of a hexagon, it will be a centrally symmetric hexagon.
Ooh. Depends. Depends on the tiling vectors that are involved. So that's a very good point. If, for example, I had made one of the vectors shorter, it would be a hexagon in that it would have 6 sides, but it doesn't have to be a centrosymmetric hexagon like so.
I mean, not a regular hexagon.
Yeah.
But with a center of symmetry. I mean, symmetry, so-called two-fold rotational symmetry.
Yeah, exactly. So as soon as you start playing with the tiling vector magnitude, you start essentially shifting and squishing some of the shapes that you're working with. And so, again, if we had this example where we've got 3 grids meeting, and you look at the 3 vectors that are involved, you've got 2 are unit length and 1 is half, then you end up with a squished hexagon along that kind of half length.
Okay, so these 3 vectors, they basically describe the boundary of a...
Yes, that's the mathematical way of defining it, yeah.
Okay.
Yeah.
Okay, yeah, thank you, Sam.
So the kind of easiest way of going about making these guys, making a quasiperiodic tiling, is to pick a set of n unit vectors, so everything's just length 1, but pick a set that are incompatible with periodicity and arrange them on a circle according to cos 2 pi j over n, sine 2 pi j over n. So they're isotropically distributed around a central point. And essentially by picking something that's not 2, 3, 4, or 6, which is what you would associate classically with kind of periodic crystallography, referencing, I think, the crystallographic restriction theorem, you're basically guaranteeing that you can tile the plane infinitely with long-range order, but it will not be a periodic tiling. So in this case, I've picked n as 5, and we return to the Penrose tiling. If we pick 8, we get what is called the Amann-Beenke tiling. But you kind of pick any number that isn't 2, 3, 4, or 6. So here we've got a 7 and 11 fold version. And you can pick any number as long as it's not those 4 that's on screen. So you could have a 99-fold rotational symmetry tiling. It would look like a complete mess, but you could have one if you really wanted one. The other kind of way of tackling creating these tilings, which I think is a bit more creative, is to actually lean into the fact that you shouldn't be using 2, 3, 4, and 6 and actually use them. And so in this case, you can pick any set of n vectors, but split them into 2 or more different families, which are scaled by an irrational number. So in this case, I've picked 6 vectors, and I've split them into 2 families, which are scaled by an irrational number. So 1, 3, and 5 would be unit length 1, and then 2, 4, and 6 would be divided by the golden mean, 1.618, which I picked arbitrarily, but comes up quite often. And just by doing this simple kind of scaling down of our vectors, we end up with 2 sets of grids in grid space that are scaled irrationally to each other, which means that any intersection is going to be irrational somewhere in that grid space. You're not going to get any repeating of the same types of intersection with a periodicity. And so that means that we are guaranteed to place tiles in a quasi-periodic manner, or at least a way in which is guaranteed to not repeat. And so as long as we pick something that's irrational, we'll always get something that is quasi-periodic. So again, I picked golden mean, but you could pick pi or square root of 3 or whatever you want to choose. By changing the scale of your grid vectors, you effectively change where you're placing the tile. So if you pick something like the square root of 100, you would have very large tile grid vectors, which would mean the separation between your tilings would be large, and you'd end up with kind of very big areas of what look like something periodic, but is actually quasi-periodic in the infinite limit. So how have I actually made these tilings? Can you make some tilings? And what about our parameter alpha? So I've talked about customizing our vectors, but I haven't talked about playing with shifts. So this is where hopefully this shows up. I'll introduce the software that I've been using to make these tilings that have been in the seminar so far. So what I have up here in the top left-hand corner is our set of tiling vectors, which at the minute are just described by our number of vectors. So if I increase this, then it just isotropically places them. Then we can control the number of grids, so we can control the size of the tiling that we produce. So in this case, we've got a small patch of the Penrose tiling. If I increase the number of grids, then we get a bigger patch. And what's cool about this kind of software is that we can also look at the grids, for example, which show where all of our tiles will be created. And we can look at the intersection points, and we can look at the types of tiles that are created at each intersection point. This shows us that, for example, we're using this intersection point corresponds to grids 1 and 4, which means we use tiling vectors 1 and 4 to make our tiles. But what if we want to make something that is a bit more exciting? We first make something that's less exciting. So again, we make our honeycomb lattice, which is not particularly fun. But then we can increase our n to then make any type of tiling corresponding to these isotropic vectors. It's very neat. But what if we want to get a bit more kind of customizable? So here I've opened up this window that shows off our grid vectors. So on the left-hand side of the screen here, we've got our tiling vectors, and on the right-hand side, we've got our grid vectors. Obviously, the orientation, as I mentioned, still stays the same, but we can start playing with the relative scale. So if I choose our grid scale for our first vector to be 1/5 of its original size, press tile, suddenly the tiles that are involved with this grid vector are being placed down more frequently than they were before, which means we start kind of smearing stuff along this direction. Again, if we look at our grid view, we can see that we've scaled down this set of grid lines corresponding to our vector. And so they're intersecting more frequently with the rest of the family. And so we get this kind of smushed together section. These guys on the left-hand side and the right-hand side that don't look like they belong is because we're actually still calculating all of the intersection points outside of this kind of squished in area. And so actually we've made a kind of very funky geometry here where we've got a smushed version in the middle, and then we've got 2 burgers buns on either side, just by playing with our grid scale. We can, of course, also play with our tile scale. So if we double this arbitrarily, these tiles are still being placed at the same position, but they're now doubled in width. And so we've got an even more stretched out version of what we had previously. And again, this is just us playing with these numbers. You can, of course, break some of the symmetry as well, if you really wanted to. And so now we're still using the same unit vectors, but we've now broken our 5-fold, 10-fold symmetry, and it's now a 2-fold symmetric thing. The problem with doing stuff like this is you get very thin tiles. And so maybe that's not particularly desirable, but the point here is that we can, customize this until we kind of get sick of it. Lastly, on the right-hand side, we've got this grid shift parameter that I mentioned, where each of these values corresponds to the shift that we're applying to each of the vectors. So this 0.2 would be shifting our vertical set of grid lines by 0.2 of a unit vector to the right-hand side. So actually, if we just put 0.4 in, maybe this will work. That's a bad view. It shifts slightly between the two. What we can do here is put it in random mode, and it will apply a random set of shifts to these vectors, to these grid shifts, sorry. Press tile, and the geometry of the tiling starts to change with each press, each time we randomize. So if I stop here, for example, we end up creating different tiling geometries with respect to the Penrose tiling. And for me, I'm very familiar with the Penrose tiling, so obviously this might not be so obvious, but we never see this arrangement of 10 thin rhombuses in the classic Penrose tiling where all our grid shifts are 0.2. So by playing with these grid shift parameters, we can produce a huge amount of different geometries just by playing with this alpha parameter. Like so. Then, of course, we can do what I had done previously, where you can take a kind of periodic seeming set of vectors, scale them by an irrational number, and produce the quasiperiodic tiling again. And again, we can play with the shifts and produce different tilings, essentially to the end of time. But I do have a note or two on this. So from a mathematical standpoint, the tiling topology of these things, so it's very well understood, and it's understood in using language that is completely beyond me. And there's no way that I'd ever be able to summarize it properly given the time that I've got. But what I want to say is that for a fixed set of vectors, so if we say that we have 5 vectors and a given value of alpha, we have what is called a tiling space. All tilings which belong to that space are what we call locally isomorphic. Mathematically, the definition is every bounded configuration of tiles that appears in any of these tilings will appear in all of the others up to translation. In an applied sense, or in a physicist language, what this means is that all points, all tilings and tiling space are essentially geometrically equivalent. Because I only care about finite patches of these things, and if that finite patch appears in every other tiling, why do I care if there's any tiny differences between the two? And in this case, all that we care about is the sum to alpha. So if I bring in our hypertiler again and look at our Penrose tiling, the sum to alpha in this case is 1. If we change this so that the sum to alpha is now 0.5, we get a completely different geometry, right? That's one thing that I've shown before. But if we were then to keep alpha as 0.5, 3, but have different grid shifts, that's not going to work. 1, 2. So that should sum to 0.5. We get the same tiling type, it's just shifted slightly in tiling space. And so all that we care about in this case is the sum to alpha. And so we do technically have a lot of customization here with alpha. It's just that it's bounded by certain kind of properties. In other words, if we want to explore what I would say individual or unique tilings, then we actually have to explore individual tiling spaces, which are accessed only by the absolute value of alpha for a fixed set of vectors. So I'm going to wrap up with the kind of lightning pitch for data science approaches to trying to find a useful quasicrystal. By asking the question, how do we know which tilings are useful, right? So if my end goal is to find a version of a tiling which is most useful in a certain context, how do I actually know what that tiling is? The problem here is that we've got a free choice of vector families, essentially, and even with the constraints on alpha, there's an enormous amount of variety in the resultant structural output that we could play with, right? I've shown that just by pressing the randomize button about 80 times, you get different structures each time. Similarly, on the other side of the coin, hand-picked tilings, which I mentioned before, that have been explored with application in mind, are essentially picked because they are popular, or in very limited cases have been carefully designed with a set of vectors that would give some sort of specific property in mind, hopefully. The problem with both of these approaches is that you never actually get to sample the full range of tiling spaces without a huge amount of time investment, right? I could sit at my desk and design 100 different tilings, and they may be useful, they may be not, but I've wasted my time in my words, by doing so. And so actually, my pitch would be for a data science approach is that we could generate, hundreds of thousands, millions of different instances of tilings that are definitely different because of the parameters that we are using to design them, but are inherently related. The idea here being that we parameterize these things exhaustively, which you can do just looking at the connectivity of different vertices, what are they connected to, and then what are they connected to, etc. And from that, you can actually derive a lot of physical properties. So looking at mechanical properties like rigidity, or looking at diffusion, looking at, again, band gaps for wave dispersion, or looking at these things as GNNs. My idea, I guess, would be that we can actually use data-driven methods, which I feel are well established now, to basically map and then invert this relationship between our construction parameters, which would be our vector families and alpha, and the physical behavior that we might expect them to exhibit. So in this case, a pipeline would be you fix your vectors, but you vary alpha, you generate all your tilings, you extract your matrix, you compute the properties based on that matrix, you build your model, and then you invert. And hopefully, eventually, we can find a quasicrystal that actually is useful. So just to quickly summarize, because I realize we're kind of rapidly running out of time. I've introduced quasiperiodic geometry. I've shown, hopefully, that even just using this one method of construction, there is a vast tunable design space, with the caveat being that the infinite limit of the mathematics of these things is very well mature. It's just the physics of the finite instances is basically largely unexplored. And that I think there is a data-driven methodology that we could use to kind of bridge that gap. Otherwise, thank you for listening.
Thank you very much, Sam. Please thank Sam for the great presentation, physically or virtually. Yes, I'll now stop the recording.